The goal of today is to inspire you. So I have a prepared slide on the digital twin development, specifically for tomato, but I will also have some introductional slides on NPEC indeed. So some of you might know me, but I'm working as a senior scientist and a business developer, which means I interact a lot also with industry or new partners for new projects. And I'm leading the construction of NPEC. I have a background in AI, and I hope today to inspire you, hopefully also to discuss some new ideas, and also to simply enable you to team up. And it could be on many different topics. You could come by, you could join our team for a few weeks or a few days. We can exchange data. So hopefully this will be a start of several new adventures. But first I would like to actually share something which is, I think, a specific challenge that we face. So we say, okay, we have technology. So also within PhenoRob, all kinds of very fancy tools are being developed. I've been in the last 20 years developing also all kinds of robot systems for dedicated projects. But my concern got bigger and bigger over time, that there were only a few innovators. And I think all of us in this room are those small group of innovators. Maybe some early adopters are there. But if we want to have impact on, for instance, climate change by screening plants, improving crops, launching new varieties, then actually there's a huge group of people that are not having the capability or not the access or not the tools to screen large numbers of plants. If we talk specifically about phenotyping tools, and this is actually the focus of our phenotyping center, but it also should also be the focus of you to say, how can I make development and technology that can be shared with larger groups of people to create that impact? And if I analyze it a bit more, then we say the innovators are often people from technology. So there's definitely a technology push towards, in this case, the phenotyping domain. But actually the biologists, they should have the tools to develop, for instance, new varieties, or come up with large-scale screening solutions that solve a very specific problem. And if I look in the timeline, actually, then as soon as you start developing tools, screen a lot of plants, then the data analysis actually becomes you could say the second bottleneck, and there we need the data science people to help us out. So this is actually the story of NPEC. We wrote it down in our proposal that we said we have in Wageningen, but also around Wageningen, we've got many brains that need tools. So let's give them a decent phenotyping center to scale up their way of working. So we proposed to our Dutch science organization, NWO, that we needed large-scale research infrastructure. So we got funded already in 2018, and we started constructing NPEC, and it's open for access. So you can come over as a research visitor, or you could make use of the tools. You can also join us to improve the tools. And I would like to zoom in today on specifically on the greenhouse, and also to come back to the earlier slides. So it is a small greenhouse focused on gathering data. And just to show you one example, here there is a collection of around 2,000 pots, and in each pot there is a different potato variety. And the goal is to figure out which of these varieties can deal with a specific fungi in the soil. And what we have basically done is we have transplanted the genotypes, we captured data, and in the earlier days they were actually taking these plants apart, screening the plants with really like hand manually driven tools, so very time consuming. But now in the new stage, it's actually pretty straightforward. We scan them with a laser scanner, we generate a point cloud. We basically get a value of digital biomass, and all the screening is fully automated. And instead of screening a set of 100 plants, we could easily go up to 2,000 or more plants. And this boosted this development enormously. And this is actually a tool that you can buy In this case, it's a PhenoSpec sensor. It spits out a value, and there's no need for a specific development of software or algorithms. So the value digital biomass is enough to figure out which variety is tolerant and which one is highly endangered actually by this fungi. Another example is actually on the field. So before I dive into the digital twin work, here too we have basically bought equipment, enabled people to use this equipment, focusing here on the drones on the field and a trade seeker, as we call it, the vehicle driving around. But just to show you how it works, we have a small team, operational team, that brings the device to a field to capture data. And in this case, it's a huge population of lettuce varieties, and they are being screened for a specific project in which many PhD students are involved. And we capture data and we hand out the data to these PhD students, and they are linking that to destructive measurements, to other elements, to genomics, simply to help them to scale up. And this is, for instance, a data set of 10 terabytes, but it's created by NPEC, handed out to users to figure out which varieties perform best. So that means we have quite a large data platform actually in place, because all these different modules, so I showed number 6, the field equipment, I showed some examples from the greenhouse, data is being uploaded, people get access to the data, and one of those bottlenecks that I described on my earlier slides is that we need data scientists to help, for instance, the biologists to deal with this amount of data. So what me as a project manager of NPEC is now doing, we have a data team that is giving all kinds of, you could say, handy tools to the actual academic users of NPEC. Then we say we acquire the data, we make sure that the data quality is good, we organize it, so we shift it around in subfolders and make sure that it's clearly retrievable, so findable. But we also develop specific tools to analyze the data. And it could be a very simple thing like this digital biomass, because if you create a number like 100,000 of files, people get overwhelmed with data actually. But if we analyze it and bring it down to numbers, then they get a hold on the data. And we also create all kinds of visualizations. Actually, it will come back in the upcoming slides, but this is simply a way to help them to get access to the information hidden in the data. And then you can do all kinds of things actually with data, and that's the main topic of today. So we have had a project finished only a few weeks ago. The title is the virtual tomato crop, and it's about digital twins. And it was a, you could say, a strategic investment within our university, where we simply explored what is actually a digital twin for us, and how can it boost our research. And it appeared to be, it was a 3-year project, appeared to be extremely inspiring actually to think about the concept of a digital twin in agriculture. So we said a digital twin is something like a digital equivalent to a real-life object, of which it mirrors its behavior and state over its lifetime in a virtual space. Actually, bringing it down into practice, that means actually that we have virtual plants which are modeled, growing in a greenhouse which is modeled, but linking this to measurements on actual tomato plants also growing in an actual greenhouse. And as soon as we interact with the models based on real-life measurements, then I think the word digital twin can be used. So dynamically updating the model based on the measured data. There are all kinds of good reasons actually to do this, also towards the applied end use. For instance, to efficiently run a greenhouse, to produce tomatoes in a resource use efficient way. And now with the energy crisis, it becomes more obvious that actually every euro that you spend accidentally on too much energy consumption could make a difference between a profitable company or not, basically. So a scheme. On the left, we have real tomatoes with real sensors. On the right, we have virtual tomatoes in a virtual greenhouse. And you could say for years, we have been doing these kinds of developments. But actually, this project brought people together that have not been together before. So the virtual plant modelers and the sensor guys actually teamed up within this project. And it's actually a loop. So we generate data here with phenotyping tools. It is processed. We want to update the model. But then the real challenge becomes clear if we want to predict what the crop will do if you would change something in reality. For instance, increase temperature, change the genotype. And that is the crucial part where the digital twin becomes really valuable. And we had many stakeholders that were very interested to think along with us, how can this be used in practice? But from an academic point of view, actually this loop was already super inspiring because it brought many people together. So we've run experiments in that greenhouse that I also just quickly showed to you. So we have 4 compartments. In this part, plants do not move. That was the example I showed quickly with scanners moving overhead. I will now focus on the greenhouse part where plants travel around on conveyors, and it enables us to capture higher quality data. So it's basically a conveyor system. Plants grow in a compartment. We try to keep the climate conditions as stable as possible. So temperature, humidity, light should be evenly distributed. But we have many replicates actually to make sure that if there are some abnormalities, that we can deal with it. So the plants grow. Actually, nothing is basically happening, but once in a while, the plants need to travel to get water or need to travel to get imaged. And just to show you how this basically looks like. So this is a later moment in the experiment. Plants need to travel, so then they are released actually from the blocker on the conveyor, and they start slowly traveling to, for instance, a watering station or an imaging station. So we had several experiments in NPEC, but I'm going to focus only on the digital twin experiments, which has been running in 2021. We had actually 4 varieties that we tested. And it was a fully automated greenhouse on the one hand, but on the other hand, we have done quite a lot of destructive measurements to capture data and link that to the image data. So some more impressions. So plants need to travel to be imaged, for instance, in one of those big white boxes to create a 3D model or to shoot a picture or a top view chlorophyll fluorescence analysis. One of the key imaging systems that we used was a 3D reconstruction device. So a plant enters the box, it is lifted on a pole, 15 cameras take a picture, and based on these 15 cameras, we can reconstruct actually the shape of the plant in this case. We use a technique which is called volumetric interception, and it spits out voxels basically, so a 3D point cloud. If you calibrate all the cameras well, you know exactly which pixel belongs to which voxel in the 3D space. And this is also published in several publications in the last 10 years. And then the challenge comes, what is actually hidden in that point cloud? Also coming back to my earlier remarks, so we can generate data, but how do you turn it into information? Now in this case, there was a postdoc, Bolaik C, who worked on deep learning to extract plant-specific elements, so leaves, stems, but also the stick and the soil, to extract information. Other imaging cabinets are also used, for instance, RGB side field, of which I will show an example, but there are more imaging systems there. This chlorophyll fluorescence imaging system was not used much actually in the digital twin project, and that's more focused on photosynthesis and efficiency of uptaking light by plants. But this is a very simple example actually of the RGB side view. So the plants grow. These are 6 views of the same plant but it's traveling around every other day, for instance, to be imaged. And then you could say that the images are actually the data, and the extracted information is actually projected here in the video. And those are very simple plant parameters like height or width or estimated biomass or something like compactness. And this is actually what I've meant. So if you are a biologist, you're completely lost if you are not able to extract information from these pictures. And then potentially this growth curve could already be enough. This growth curve shows that this specific variety grows in a certain speed and another variety grows in a different speed. So what we do with an NPEC, we hand out the data, we hand out CSV files with the information in it, but we also hand out these videos visualizing the development of the plants over time, just to make sure that they get a grip on the data. And still we had a big team of people doing all kinds of destructive measurements on the plants for ground truthing, for training the models, also training the AI. Katarina Streit, one of the leading postdocs of the Digital Twin project. Second part is the virtual tomato crop. And this is actually, you could say, a different group of people that have been working on, for instance, how to model a greenhouse. So taking into account the cover, the materials, the air treatment units, which screens are there, which illumination, LED or something else is there. Whether outside forecast, but also historically, everything is taken into account, and they can already predict plant development over time. But we want to do this more specifically based on plant measurements. And there are many sensors actually in the greenhouse to capture what's happening to those plants, so light, humidity, temperature, CO2, etc. So that's one part of the modeling. So we have been able to model the greenhouse using a tool called Kaspro, also published, so you can Google for it and you can find information. And on the other hand, we have a crop growth model in place. And this crop growth model was developed also by Katarina Streit and her colleagues. And it's very focused on light interception. Now what you see here is actually a 3D model captured by the 3D system that I just showed to you. And then there is, the colors represent actually the amount of light coming onto the leaves from a specific point in space. Could be the sun, could be an LED source. So the higher the value, the more light enters into the canopy onto the leaves. And you can also scale it up and say, if we have a canopy, multiple plants, if you put them more closely together, the lower leaves get less information or actually less energy. If you put them further apart, you will have plants that grow faster, but the overall yield of your greenhouse is lower. And then we had, on the one hand, values of measurements, so the observed, for instance, organs, or the observed dry weight, observed plant height, and on the other hand, a model that was actually predicting the development. So here you can see the virtual plant model growing over time. And this is the key element of the project. So we got sensor readings, we got measurements, we got a virtual greenhouse, virtual plant in place. Let's now try to tune the models from actually both dimensions, virtually and for real. And then, for instance, we have been changing the virtual plant parameters, for instance, effect of temperature or the effect of light, to make sure that it linked with the measured data, so the observed and the fit. For instance, for the internode length, because the plant height is determined on the individual internode length. And just to visualize this, we have turned our entire greenhouse into Unity. And there was actually quite a quick win in visualization. So this is, you can say this is not actually the digital twin, but this is more like a visualization, how everything could come together, and also how to share insights, information with potentially growers or end users. So you can see the actual 3D space where plants grow. These are the virtual plant models Katarina Stuyt developed. This is the actual greenhouse 3D CAD drawing that the greenhouse manufacturer gave to us. This is the conveyor system. So the conveyor supplier gave us this 3D drawing. Here are sensor readings, and this is the virtual plant model. And if I would play around basically in this 3D space, then it's interactive. So actually the greenhouse is located on our campus. So these are the campus buildings that we also added to Unity. Basically, a why not idea. But if we zoom into the greenhouse, then we can see the plants growing specifically there. It's just like a normal day actually in the greenhouse. And then we can do all kinds of things. So we can visualize the collected information of leaf area, for instance, measured by the imaging systems, or in this case, as was predicted by the virtual plant model. We can load 2 different genotypes. We can let the actually plants virtually grow by changing the time. But there's more. So we can also calculate the amount of light falling onto the leaves with this specific plant density setting. And we can play around also with changing parameters, going back in time. But also the sun, for instance, is having a certain position in the sky. So there might be some shading issues, or there might be some reasons why certain plants in certain locations grow differently than on other locations. And it also helps us to explore why certain data, maybe abnormalities or odd situations are occurring. I need to be a bit brief here, so I will wrap up also to enable you to launch questions or come up with suggestions. So just to wrap up the digital twin idea, so this is the first sentence I also read out loud. So hopefully we can increase the resource use efficiency of greenhouse production, for instance, of tomatoes or other crops. So this is also linked to the concept of an autonomous greenhouse. And it can be, just to be very specific, so we can predict crop yield and also predict energy usage using this real-time crop monitoring and greenhouse data. We can help growers to determine leaf pruning strategies, or maybe the planting layout or plant density decisions. We can explore options for plant varieties, but also which plant traits are useful to take into account for the digital twin. If you want to build a new greenhouse, we can support and do calculations on the effect of lighting, effect of glass type, and greenhouse construction. And this is linked to autonomous greenhouses, so optimizing greenhouse climate control by actually listening to the crop, placing sensors strategically, for instance, in what you see in the background image around the plants. And future work, more from a technical point of view. So one challenge, of course, is we have been doing this in NPEC greenhouse, which is a phenotyping center focused not on growing plants, you could say, but more focused on generating data. So how do we translate this approach to an actual production greenhouse? And I think I've said it several times, but data is definitely a burden. So we need to extract information. And there, I think all of you could definitely help us. You know, you need AI, you need software developers, you need to have good sensor quality. So it's definitely a technology required here. And we should explore together. And together means actually also with breeders, with growers, with suppliers, which information and which traits should be extracted. We should develop tools, like a few of the tools that I showed. And if we have a new user, we need to share the code so he can jump onto something that has been developed by the earlier users. And that's also one of my ambitions for this year. So NPEC developments are now focused. So we've spent all the money in buying the equipment, but we completely focus now on data enrichment, data processing, and data visualization. Thanks. So if there are questions, ideas, please let me know. I shared work from many of my colleagues, actually. We try to put all the information that we have on NPEC on our website. And these are two pictures of the official opening of NPEC that we did last September. Maybe a few of you were there during the first day of the International Plant Phenotyping Symposium.